Welcome to pattern analysis. We talked today about Markov random field inference through the lens of energy minimization, and we will be using graph cuts for this. So, recall that we had, or we at least briefly mentioned, the Hammersley-Clifford theorem, and this established a connection between our probabilistic formulation of a Markov random field, where we have independence assumptions to factorize a joint distribution. And the Hammersley-Clifford theorem linked this to a so-called Gibbs random field, which is a field of clicks in a graph that have potentials. Yeah? And in particular, these maximal clicks, like fully connected subgraphs, were relevant, even though we only look at clicks of size 2, so it's not, it sounds greater than it actually is. But anyways, so the nodes in a click, so let's denote this as fancy C. These nodes, they are valued in a potential function that is of the form e raised to the power of some energy term, where the actual nodes are an argument to that energy term, h of c. This energy term, it can be seen as you can say like a measure for compatibility between different nodes or choices of labels, if we think about the original MRF task. So a lower energy means better compatibility. Okay. And then we said, okay, look, there's this simplicity that if you want to encode a task, you only have to define a potential that has a maximum at a different location, which corresponds to having an energy term that has a minimum at a certain location. So it's clearly easier to use than these like probability distributions. This is all fine and it's correct, but there's another aspect that comes into play. And this is that having a framework that allows to use energy functions also allows to use energy-based optimization techniques. And there's a lot of literature on this. And this is what we will be following up on today. So there's a very influential paper, thousands of citations by Kolmogorov and Sarbi, with the title, "What energy functions can be minimized via graph cuts?" So the title is already like the program that is relevant or interesting for us. The reference is down there. I also uploaded the paper to StudOn. And in that paper, among other things, they show that these energy functions that come from our click potentials or that come from Markov random fields, more generally speaking, can be directly mapped to a graph cut solution. So let's study this a bit more. We will first look into graph cuts. This graph cuts, maximum flow is essentially the same thing, and this is a topic from like your undergrad data, like algorithms and data structures class, so most likely you're familiar with this, but I'm quickly summarizing this, recapping on this. And then let's use this technique as an optimizer. And in order to feed it with a proper task, we need to look into a transformation of this click-based optimization goal to an equivalent task for the graph cut, such that if we solve the graph cut problem, we also solve the underlying click-based optimization. Okay, so let's have a look into maximum flow, minimum cut. So what is the maximum flow problem? It's a like standard combinatorial problem. It has a polynomial time solution, so it's efficient. we are given a graph with positive edge weights, source node and sink node. Source node and sink node are two artificial nodes, and then there's the graph in between. Yeah, and we will denote, so here's a graph already. The source is S and the sink is T. Yeah, okay. Now the task, and other nodes are in between, edges have weights, and so on. So the idea is this, or the backstory is this. So let's say the edge weights correspond to tube capacities. Yeah? So we want to determine the maximum possible throughput of some water, for example. This is the flow from the source S to the sink T per time unit. Yeah? So let's have a look. So here we have a capacity of 3. Here we have a capacity of 3. Here we have a capacity of 3. So we can already, like just by looking at it, we could say, okay, let's pump 3 units here along this road, 3, 3, 3. This brings 3 units of water from source to sink. Yeah? And we can check down here, we have a capacity of 5. Oh, but here we have only a capacity of 3, so probably we will only be able to pump 3. No, here we have only a capacity of 1, so we have to further throttle it down. It's just going to be a capacity of 1, certainly, on this down path here through the graph. But okay, so then it means we have a throughput of 3 on the top lane and of 1 on the bottom lane, and you can annotate this as shown on the right. So we use 3 out of 3 capacity here for the top tubes. This diagonal tube, we don't use it at all, so it's a 0. And then we use 1 out of 5, 1 out of 3, 1 out of 1 here for the bottom link. Yeah. So why are these ones here printed in red? Because these are tubes or pipes where we fully use the capacity. Yeah. So, and there's an analogy between maximum flow and minimum cut. So what is a minimum cut? A minimum cut is the set of edges with minimum weight that separate S from T. And what we can now take is, we can say we take edges that are red to form the minimum cut. Like for example, here's a red one and there's a red one. So if we cut here, the edge weights are 4. So it's a cut of weight 4. No? Or we could also cut here. So this is also this edge of 1 and edge of 3 is a weight of 4. We will also be able to cut here because there's a special rule. This edge goes from the side of T to the side of S. So A, like with respect to this cut here, if we check, A is on the right hand side, so it's on the side of T, and this edge here, it goes from A to D, so it goes backwards from the side of T to the side of S, so it doesn't count. So this cut is also a cut of weight 4. The other cuts are not minimal because the pipes here have bigger capacity, like 5, for example. This alone makes it already more expensive. Or here the 3 plus some 3 from top here also makes it more expensive. Okay. So yeah, so the min cut, sorry, here's the explanation. So the minimum cut is the smallest sum of edges that disconnect S and T. Yeah? Max flow, min cut are identical. A min cut is easily found by selecting a minimal set of maxed out edges that disconnects S and T. So, like for example, we have these 3 ones as discussed here, and this one here, and from that, if we only form all combinations of these edges, we can find the possible minimal cuts here. No? Okay. There are multiple solutions, yep. In practice, you just select one of the solutions. It's usually sufficient, like whatever you want to do with that. Okay. So, how can this maximum flow problem algorithmically be solved? There are several algorithms. Arguably the most well-known algorithm, and probably the one that you discussed in your algorithms in data structures class, is the algorithm by Ford and Fulkerson. So how does it work? You search for a shortest path in a greedy fashion, like without any particular considerations. Then you max out the flow capacity along that path, and depending on how much you can, like how much capacity you have along that path, you reduce the edge weights accordingly. And then there's a special trick, yeah, because we greedily select the shortest path. It could be the case that there's a not optimal choice that blocks some other possibilities. So in order to undo a non-optimal choice, what you can do is, or what you have to do is to introduce a backward edge to undo, let's say, dead ends that come from that greedy optimization. And then you repeat, yeah? And you repeat until there's no path left. Let's go through our specific example of our ST graph. So let's say we find, like, the first shortest path that we find is this path length of 5. Now let's look at this path with respect to flow capacity. So here's a 3, here's a 1, here's a 1. So we can send a flow of 1 through this path. Yeah, so we have a path flow of 1. And maybe it was not a good choice. So in order to prepare a provision that we can undo this, here in green, backward edges along that path are inserted with a capacity of 1, such that we could undo this choice by sending something in the opposite direction. No? Okay. So here's the resulting graph. We again search for a shortest path. And maybe we find this path here, from A to C to T. If we look at this in terms of maximum flow, so the path length is 8. If we look at this in terms of maximum flow, we see we can send at most 2 units of water that way. So let's do it. And we have to insert the according backward edges. So here we have already a backward edge of 1. So this adds up to a backward edge of 3. Residual capacity is 0. Here we have a backward edge and here of capacity 2. And we're done. Continue. This is the replacement graph. We again search for a shortest path and we find this path. Zack, zack, zack. It looks complicated. But here we actually use a backward edge. So we are undoing a choice from the past by going, like in the past we sent some flow in this direction. Now we follow the path in the other direction, backwards. That way we undo it effectively. Yeah. Okay, so let's check what is our flow capacity. We have 5, we have 3, but here's only 1. So all here is 1. So we can send at most a flow of 1 along this direction. So we properly update our backward edges. This becomes a 1 here again. This backward edge kind of vanishes. Okay, and we're done. So the total, so there's no, why are we done? Because there's no further shortest or no further path from S to T. So the zero edges mean there's no path. So you cannot use these edges. There's no link anymore. The total flow is, we had 1, then we had 2, then we had 1 is 4. Again, what we already saw on the first slide. The minimum cut includes the edge between D and T, for sure. This we need to cut. And then any of the edges up here. So either this edge or that edge or that edge. So any of these edges disconnects the paths from S to T. Yeah? Okay, so the 4 sets of equivalent minimum cuts are the edge from C to T and D to T, the edge from A to C and D to T, and the edges S to A to D is a backward edge, and then D to D. D to T, sorry. Okay. Okay, good. So yeah. So for small graphs, I mean, it's and particularly if we just draw it on a blackboard or something, you don't need to execute the whole algorithm. No? Oftentimes, just by looking at the graph, you see, okay, there's a bottleneck here and so on. And you can directly write down the max flow or min cut. But the way how we will be using this now is that we will construct a graph in such a way that the cost for certain choices of node labels are transformed into costs of a minimum cut through the graph. So let's do that. Markov random field inference via minimum cuts. So let's start with the Markov random fields. Yeah? So we said, okay, there are labels in this variable set, Z1 to Zn, and we are interested in the optimal labels. What means optimal? We want to maximize, if we do the transition to the Gibbs random field already, we want to maximize the value, the product of these click potentials, going over all clicks in the graph, moderating this with the partition function, which we can't evaluate because exponentially many terms, but anyways. So these are the labels that we want. If we maximize this expression, what are the labels that lead to that maximization? Now, if we expand the click potentials, it means we have a function e raised to the power of minus a sum of unary energy terms, so energy terms between observations xi and hidden variables zi and pairwise energy terms, so potentials with these pairwise energy terms, e raised to the power of minus a sum of these energy terms between two hidden variables, ci and zj. Yeah? And of course we can write this in one exponent, so then it's just e raised to the power of minus the sum of the unary energy terms and the pairwise energy terms. No? Okay. Okay, so the exponentiation is a strictly monotonous function. So we can say if we look for the maximum solution, this is just the same as if we look for the minimum solution for these energy terms. Yeah? So we can just write the optimum labels are those that minimize the expression of the sum over all unary energy functions plus the sum over all pairwise energy functions. Yeah? That's just like that. And this is an energy function in the sense like where there like a lot of energy, like a lot of theory exists. Yeah. Okay, so there's a large body of work on the minimization of energy functions. And Kolmogorov and Sabi, the authors of the paper the reference somehow died. I will fix this. But the paper is also on Studon. They systematically show what types of energy functions can be minimized with graph cuts. So the energy function that we just saw, like the sum of unary terms and pairwise terms, is sufficiently generic, we can say, such that it's well solvable with these like graph cut tools. And the idea is to transform the original maximum likelihood problem to find a labeling that maximizes the potential functions to an equivalent minimum cut problem. Like if we want to phrase this as natural language, it could be something like assign labels in such a way that the changes of the labels cause a minimal loss. Yeah? Okay. And we achieve this by constructing a directed graph with edge weights that are chosen in a particular way. So this is what we will be discussing. Some constraints. The construction only works for binary labels. So I'm just writing binary labels could be anything, but I'm just going to write 0 and 1 to keep things simple. Yeah. We will, at the end of this lecture, we will see an extension to non-binary labels. But here's binary. Yeah. And here we have a hard constraint. This is these are all hard constraints, but anyways, so the maximum click size shall be 2. And we also have to require the so-called submodularity condition, which means if we look at the energy, I should define this. So this is the energy between two hidden variables. It's a pairwise energy term, so it has to be between two hidden variables, where both variables have value 0. And in the same way, this is the energy between two hidden variables where both variables have the value 1. And the energy of those two configurations where we have the same label shall be lower than the energy of the two possible configurations where these two labels have different values. So that means, in general, the pairwise energy term shall be of a construction where it's better to have identical labels. Yeah, it's a smoothness term. Or if you go from a different area, like if you come from the optimization direction, it's like a regularizer. No? You say, okay, like simpler, smoother solutions, they are better. No? Okay, and the submodularity condition kind of enforces this. So it doesn't say every single term needs to be lower, but instead the sum of the two equal label configuration needs to be lower or equal than the sum of the two different label configurations. Yeah? So it's a bit relaxed, but other than that, it's the same thing. So we prefer identical labels in the pairwise term. Okay, so if these three conditions hold, the binary labels, maximum click size of 2, and the pairwise energy terms, then the algorithm that we will be looking at will find a globally optimal solution, which is a guarantee that we rarely have in this lecture, in polynomial time. So it's really good, in other words. Here's an idea. Oh, here's the construction idea. Let's have a look only at the hidden variables. So here we have Z1 and it's somehow connected to Z2 and Z4 and so on. So it's a grid of hidden variables with relationships to the neighbors, much in the sense of the previous lecture, just that we didn't draw the observations. If we want to draw the observations, we would have to put another variable in here. But let's omit this for the moment. So we have a grid of the hidden variables. And the idea is this, that we introduce a pseudonode S, which will be the source of the graph cut, and a pseudonode T, which will be the sink of the graph cut. And conceptually, so we will save some edges later, but conceptually, we would connect every hidden variable to the source and to the sink. Yeah? And then with a certain weight. Yeah? So it's not really clear what this weight shall be. We will discuss this in a second. Yeah? Okay. But then, based on these weights and so on, you can calculate a graph cut from between source and sink. And this will lead to a certain set of edges that are maxed out. And if we say, okay, indeed, let's take this literal and let's cut the graph in half, like along these maxed out edges, then it gives us two parts or multiple parts of the graph, where one part is connected to the source and one part is connected to the sink. So now if we say, okay, all nodes that are linked to the sink, they shall receive the value 0, the label 0, and all nodes that are to the source, all nodes connected to the source shall receive the label 0, all nodes that are connected to the sink shall receive the label 1. Then we have a labeling for all the hidden variables. Yeah? Because if it's a minimum cut, it literally cuts the graph into two parts or multiple parts, but it disconnects every node either from the source or from the sink. So for every hidden node here, we can assign a label of 0 or 1, depending on where it is connected to. Okay. So this is the idea. Now all the magic is in the choice of these weights W1 and W2. And this is what we need to study. And once we have these weights, we can just feed the graph to the graph cut solver and we get the solution. It's a fully automated process in polynomial time, globally optimal. Okay. So how to choose the weights? We can use a little trick. And this is really important to make the life easier here. And this is an additivity property. So the equivalence between the Markov random field inference and the graph cut is ensured by the construction of the edge weights. And the very nice construction property is that every individual energy term, so every energy term can individually be transformed into a graph, a little piece of a snippet of a graph. Yeah? And this works because there is a homomorphic relationship between like the whole graph and a part of the graph. So let's have a closer look. Energy minimization via min-cut is homomorphic under graph composition. So if a graph G1 encodes the minimum of an energy term E1, and if a graph G2 encodes the minimum of an energy term E2, then I can form the union of graph G1 and G2, and this will encode the minimum of energy term 1 plus energy term 2, which is beautiful. Let's quickly go backwards. Here we do have a sum of like this is a sum of energy terms, this is a sum of energy terms, this is a sum of energy terms. So we do have sums of energy terms here. And this homomorphic property here allows us to encode for every little energy term the optimization goal, and then to form the union of these graphs. What is the union of these graphs? Well, if there are different hidden variables involved, it's not a problem. We just set them next to each other. But if the same variables are involved, we have to add the edge weights. Yeah? So if both graphs have an edge, let's say between source and hidden node set I, and both have a certain weight, then we just add these weights together. You know? Okay, and this is really a powerful property. So if you encode each single energy term to a graph such that the graph's minimum cut encodes the minimum energy, then also the minimum cut of the sum or union of all individual graphs will provide a solution to the minimum energy of the sum of terms. Wow. Yeah. Okay. So let us now look for optimal encodings of these individual energy terms. So let's have a look at the unary energy terms first. So we want to encode an energy term between an observation and a hidden variable. Yeah? Being connected to the source corresponds to an assignment of the label 0 to the hidden variable zi. Being connected to the sink corresponds to an assignment of the label 1 to the hidden variable. Yeah? So how can we make this a graph cut problem? We can say, okay, not a problem. Here's the sink. Sorry, here's the source. I blame it to the heat. Here's the source. Here's the sink. Here's our hidden variable. And if we would cut here, yeah, if this would be the minimum cut, if it would occur here, then Zi would be connected to t. T has the value 1. So we would effectively assign a value 1 to this hidden variable. So it means that cutting here would have to incur the cost of assigning a label Ci equals 1 to this unary term. Yeah? And the observation here we just plug in the observation like whatever we have in our task formulation. For example, for the denoising task, we would just put the original pixel intensity here. Is it black or white? So we put this in here, and the cost for cutting here would be to have a pixel of intensity xi and assigning a target intensity of 1. Yeah? And symmetrically, if we say, okay, we want, what if we cut here? So in this case, the source has the value 0. So cutting here means Zi is on the side of the source. So Zi obtains the value 0. So the cost of this cut, so the edge weight here, yeah, has to be so as if we would assign to the hidden variable the value 0. So y, sorry, not y, but Zi equals 0. Yeah? Okay. So this is why we have the 0 here. And here for the second part of this energy term, we just put in like whatever observation we have in the image. Yeah? Okay. So then we have a weight here for this term, weight for that term, and we could say here's a full-blown graph, minimize this, and it would, I mean, if this is the only constraint, literally it would just select the lower energy, which is probably the one that does nothing. It just preserves the pixel intensity, assigns the same intensity as the input pixel to the output. But it's fine, it's still a valid optimization. No? If we have it like this, we can say, okay, look, this is a bit redundant even. Yeah, we can save one edge if we add a pre-processing step. For example, if the energy for assigning 1 to the hidden variable is larger than the energy for assigning a 0 to the hidden variable, maybe because the observation is also a 0, then it should be cheaper, no? To have a hidden variable that agrees with the observation should be cheaper. Then we can say, okay, look, we can save one edge here, to put no edge between Zi and t, and just put an edge of the differences in energies here between the source and Zi. Yeah? Because assigning a 1 here would be more expensive. If we would cut here, would be more expensive than assigning a 0 here. Or if the situation is different, if the observation contains a 1, it could be the case that this energy term for assigning a 1 to the hidden variable is lower than assigning a 0, and then symmetric, exactly symmetric to the above construction. We could say, well, okay, let's only keep this edge here. So here we need an edge with the difference between the cost of assigning a 0 versus the cost of assigning a 1. Okay. With this, we can save edges, so our max flow will run faster. But of course, the offset of the minimum energy, it changes a bit because we are not encoding the very original energy terms here, but instead like these difference terms. But that's just a minor detail. What about the pairwise energy terms? The pairwise energy terms are fairly complicated, but one thing after another. So we have a source, we have a sink, and pairwise energy term means we have an energy between two hidden variables. So this is our regularizer, yeah. But it means that as a graph primitive, we have two hidden variables involved, a variable Zi and a variable Zj. And we have 4 types of possible cuts. Yeah? So here's one possibility. We could assign value 1 to both variables. Yeah, then we need to cut off the source. Second possibility, we have to assign value 0 to both variables, then we have to cut off the sink. Or we could have a mix of both, so we could either assign a 1 to zi and a 0 to zj, or the other way around, 0 to zi and 1 to zj. And in that case, it goes a bit diagonal here. Hold on. So we would cut in such a way that zi is connected to one of our terminal nodes here and zj to the other one. Okay. Now if we want to calculate the edge weights, we have a little problem. We have 5 edges, but we have only 4 terms. So it doesn't really add up. What are the 4 terms? These are the 4 energy configurations. But what one can do is to form an equivalent smaller graph following similar considerations as for the unary potential, that we said, okay, we don't need to encode the absolute energy terms, we only need to encode the differences in the energy terms. Yeah? And such an equivalent smaller graph then consists of 3 edges and an offset, so we have 4 unknowns and we have 4 terms. So everything is fine and it can be solved like we can solve for the actual edge weights. The actual construction is a bit complicated. I inserted 2 pictures on this and the next slide from the paper to illustrate the calculation, but I will not request you to perform this calculation on your own. Yeah? But just for illustration how the reasoning works. So if we have a pairwise energy term, we can have these 4 configurations. We already talked about it. We can assign 0 to both, we can assign 1s to both hidden variables, or we can assign mixed labels to both hidden variables, 0, 1 or 1, 0. So let's denote these configurations as A, B, C, or D. And then there's a little trickery happening. So if you have these terms A, B, C, and D, you can say, okay, I rewrite this. So I say I have an offset A, which is just the energy of having identical 0 labels for both. And I'm looking at the difference between C and A. C and A means I have a label of 0 assigned to the second variable, and the first variable, this may change, and depending on what the change is, I enter this change here. And this is an example for the case that C is actually has a higher energy than A, yeah, which makes sense. These are different labels. Okay, and the second example is that C also has a higher energy than D. Yeah, so I can look at the difference between D and C, which means the first variable is fixed to 1. And I only look at a difference in the second variable. How does my energy change there? And then in order to actually make this an equation, it's a bit weird, but I need a correction term, which is B plus C minus A minus D. So, and then if I add all these terms together, I end up with exactly A, B, C, D. Okay. Following that consideration, I can say, okay, so from the unary potentials, I had this idea that I can only use one replacement edge if I have a change in a variable between 1 and 2. It can be either up here or can be down there. And for a pairwise term now, I can similarly track a change in one variable by fixing the other with one such edge here. Yeah. So here for C minus A and here for C minus D. And then I need a cross edge between these two hidden variables with this remaining cost term B plus C minus A minus D. Yeah? Okay, let's quickly read the caption. So this is again from the paper, the picture. Graphs that represent some functions in this space of energy functions that consist of two, like unary and pairwise potentials. Sorry, it didn't define this. A, the graph for a unary potential where the assignment of a 0 to the hidden variable is larger than assignment for 1, the energy. B, graph for unary potential again, where this is not the case, and then third edge for this pairwise term, and here in D we have a complete graph for the pairwise term for the case that C is larger than A and C is larger than D. Yeah, okay. And depending on how these that C is larger for A and C is larger for D, I think this holds for all image processing problems, at least that I'm aware of. So you can use this graph as a fixed template, I think, for all your homework in a way. No? But if you would have a different cost structure, then you might want to repeat all this reasoning, which I just coarsely outlined in order to fix your graph. No? Okay, but we won't, I'm sure we won't need it. Okay, but to wrap this up, so let's say we have one of these many problems where these conditions hold. Then we can say, okay, let's form this like simplified graph structure where we have three edges here connecting two hidden variables and the source and the sink of the graph, and we can plug in these edge weights by effectively plugging in the results of that equation, so the differences of these energy terms. Yeah? Okay. Yeah, and then so now we have a way of encoding unary energy terms. We have a way of encoding pairwise energy terms. So we can do this for all hidden variables, like for all energy terms in this equation, add this together to a total like super graph and calculate the min-cut. And then this runs in polynomial time, polynomial in the number of hidden variables, and finds a globally optimal solution. So the single best solution that is out there, which is really nice. Now we said, okay, this only works for binary labels. What if we have a more general task? Yeah, like non-binary labels, for example, some image processing task. We want to assign different gray values or even colors or so. No? Okay. Here is a generalization of the algorithm, and it's called, the method is called alpha expansion method. It's not globally optimal anymore. I'm going to talk about this in a minute, but this is how it works. So we have a set of labels, label values, yeah, and they are more than just 0 and 1. And from this set, we just select one label, can be random, or we can visit them in some order. So now we have a label alpha selected, no? Maybe 2 or 3, or whatever. Then we convert the task into a binary task according to this label alpha. So this is done in such a way that we say fix the hidden variables that have label alpha. Yeah. So these are just constant terms now, and we do an optimization for all the other hidden variables. Yeah. So this is a one versus all type of labeling situation. So we say, let's make a binary task where we can either assign the label alpha to each hidden variable, or keep whatever label we have. Yeah, and we run a graph cut for that, but not for those variables that already had the alpha, but only for the remaining variables. So, and then we select a solution with the lowest energy that switches at least one other hidden variable to the variable alpha, like whatever the cost is. Yeah. So we take that solution with the minimum cost that switches at least one variable towards alpha. And then we check, like, was the amount of energy that we needed to convert this label to alpha, is it higher or is it lower than the energy that we had before? No? If it leads to a lower energy, we keep it. If it's a higher energy, we don't do this. No? So in that sense, it's a greedy procedure. Yeah? It's a greedy expansion of the labeling. And then you probably are already suspecting, okay, like such a greedy search strategy in this context, it cannot give a globally optimal solution. If you think so, you're right, it's not globally optimal anymore. But it's not too bad. So the alpha expansion is within a certain margin of the optimal solution. This provably. So in that sense, the solution oftentimes is good enough. Here's a little illustration here from, I think, a semantic segmentation example, an example of an expansion move. I took it from the paper. The labeling on the right is a wide expansion move from the labeling on the left. So apparently the label that we picked was wide, so they are fixed. And now we seek for the lowest energy solution that switches at least one label. And here apparently we switched 4 labels, 1, 2, 3. So the black, the gray, and the other gray here. And here, if this is one label, then so it's at least 4 labels that were switched. And then we check, okay, does this lead to a lower energy? Then we keep it. Otherwise, we forget about it, and we repeat this in a loop for different labels. And at some point, if for a while there were no improvements, or for one round of labels, if we don't find further improvements, it stopped. And this is the final solution. Okay. But this is just a hack, let's say, to permit the use of multiple labels. I think the really interesting part is the construction for getting a solution for a single, like a binary labeling case, as we discussed it earlier for the encoding of the unary and pairwise potentials. Okay, with that, we're done for today. We can further discuss this, of course, in our joint meeting. I'd like to say thank you and see you soon. Bye-bye.